So, what we shall do is we shall first generate a signal that consists of two sine waves, an example that we have seen earlier. So, let us do that. Okay. Okay. So, let us do that xk. So, we have generated a signal that consists of two sines running in parallel of frequencies 4 and 15 hertz respectively. The first step in the computation of scalogram is the computation of the CWT itself. For that we need to supply the set of scales over which we want to compute the CWT. So, let us set the initial scale as 2. Let us assume that the sampling interval is 1. You can always rescale the scales with the appropriate sampling interval. Just to make things simple, we can say S naught is 2 and then our scale vector we can probably compute it up to log 2 of n by 8. Or maybe even run up to n, that does not matter. Okay. And let us choose this as our set of scales over which we want to compute the CWT, and now compute the CWT. We are using a convolution algorithm here, we are not really hard pressed for time. So, let us use the convolution algorithm, and in fact the scalogram routine, that is the W scalogram routine in MATLAB's wavelet toolbox, assumes that you have computed the CWT by using convolution algorithm, but nothing prevents you from using the CWT based on Fourier transform algorithm and passing that to scalogram. So, the W scalogram is not going to break down. Okay. So, now I have this coefficients computed from the CWT, and all I have to do is now plot the scalogram. What I shall do is I shall first issue the command and then go over quickly the help. So, what I am doing here is I am using of course a W scalogram routine which is bundled with the MATLAB's wavelet toolbox, and in the first argument I specify if I want a contour plot or an image plot. This W scalogram is capable of returning the computed scalogram values. Right now I am not taking that, I am not asking for the scalogram as the output, I just want a plot of the scalogram and I want a contour plot. The first argument, the second argument is a set of coefficients that you have computed from CWT. This could come either from your CWT or the Fourier transform based algorithm. The only difference is if you have computed using the convolution algorithm, then directly you can pass the output of that here as your second argument. But if you have computed using the Fourier transform based algorithm, then remember that it returns a structure, therefore, you have to access that specific field and pass it along, that is the only difference. Then the remaining arguments are optional. So, for example, I supply the vector of scales at which I have computed, and I do this by specifying this scales property, and if I do not do that, then it assumes that you have computed from certain set of scales and so on. It is better to always pass the scales at which you have computed, and then I also plot the I also pass on the signal to the scalogram. Now, this is again optional. If I pass the signal, then it plots the signal on the top and the scalogram at the bottom. It makes your life easier when it comes to comparing the features pointed out by the scalogram and the features present in the signal. And here I can pass on also the time vector at which I have computed, and for this I can specify by specifying the x data property, and that is our time vector, and the final power that I have is 0.5. What is this power? Well, it is essentially got to do with the normalization. Remember, this amounts to the normalization of the scalogram amounts to scaling the coefficients, CWT coefficients, by 1 over root s. So, this power is essentially the 1 over s raised to some power, and that power is 0.5 if you want a normalized scalogram. If you do not want a normalized scalogram, then do not pass this argument, then by default the wavelet coefficients are not renormalized. So, let us look at the unnormalized scalogram and see what plot is obtained. So, this is the plot that we have. So, look at what we have here, the signal on the top and the scalogram here. So, what has happened here is, of course, you should expect the scalogram to be intense around 2 scales, right. These 2 scales, when you convert them into frequencies, you will be able to find the appropriate frequencies. You can use the conversions that we have done from scale to frequency. But what comes out from this unnormalized scalogram is somewhat misleading. It says that the signal at the higher scale, I have asked for a contour plot, higher scale would correspond to a lower frequency, that seems to have more energy than the one at the lower scale. Now, this is in line with what we discussed earlier. The wavelets at higher scales take in more of the signal at any tau, and therefore have a larger value for the coefficient compared to the wave coefficient obtained by wavelets at smaller scales. Now, what we shall do is we shall normalize the scalogram and see whether it makes any difference. So, now things have fallen somewhat in order, that I have now the scalogram showing me that the energy of the signals, that which is essentially the sinusoidal components at both frequencies around both scales are of comparable, are comparable, the energies are comparable, right. So, this makes now a lot more sense considering the way we have generated the signal, right. So, and you can also obtain an image plot which probably looks more colorful. The contour plots do not look so colorful necessarily. So, the image plots make it look more drastic, but notice that whenever you plot an image plot, the scales may be reversed, because images are usually produced in such a way that the y axis is reversed. Okay. So, keep that in mind. So, hopefully now you understand the difference between normalized scalogram and unnormalized scalogram, why you should be working with normalized scalograms. Let us also look at the scalogram of an impulse. Before I do that, let me take you to the documentation on the scalogram. So, here is our documentation. I am not sure this is clear to you, but what it says is essentially the default syntax. What is the default syntax and what it returns? It returns essentially the scalogram computed at different scale values and tau values, and the optional arguments as well, and then what is this what is the default value for those optional arguments, and that's about it. Essentially the power is something that the power is something that has got to do with how you scale the coefficients. With the normalization that we have chosen, we normalize the coefficients with 1 over s power half, and that half is the power that it is talking about. That is about it. So, let us now generate an impulse of first let us have a vector of length 200 and let us arbitrarily pick a value at which we want an impulse. Let us say the value of the impulse is 5 at 80, we could choose a pulse as well, but that is what essentially. So, what we have here is a pulse sorry an impulse located at 80th instant. Now, we want to know how the scalogram of this impulse looks like. So, I have xk2 underscore CWT coming out of the continuous wavelet transform routine. We can use the same scales, that is advantage of working with sample data, that is assuming sampling interval to be 1. But of course, the length of n is different. So, let us recompute length of xk2 S naught is the same in both cases, that is the starting scale is the same. So, let us compute the continuous wavelet transform xk2 CWT is CWT xk2 and scale, and we shall particularly use a complex Morlet wavelet. So, that is what we have now, and we go back and here change our time vector as 1 to 200 and change the signal to xk2 and change the wavelet transform to see what is happening. Well, we have computed at more scales than necessary. We can go back and actually change the scales up to which we are computing, or alternatively change the limits for the y axis here on the image plot. We can also do a contour plot if you like, but let us change the limits here. First, you can determine what the limits are. So, these are the limits. We can change these limits to 0.5, let us say to 10. Yeah. So, now we are able to see the scalogram. Of course, we have not computed at a very fine set of scales, and therefore, you see this square boxes. We could recompute this at very fine scales to get a very fine display. So, to do that, we can go back and change the spacing here for the scalogram, and we can ask a 0.05 spacing here, of course, in terms of powers of 2, and then recompute our continuous wavelet transform and replot our scalogram, and we can actually further so, this is the situation that we have here. We could yeah. So, in fact, you can play around with the y axis limits, but an important point to observe here is as you are moving the scales here, let me even change, I do not know if you are able to see the font size, I will change the font size for you. So, as we are moving up the scales, in fact, we can move up further. What is happening is that the energy is spreading, and that should be expected because the wider wavelets, that is the wavelets at higher scales, result in a larger smearing in time, right. Therefore, the ability of the wavelet to detect the or to localize the energy in time deteriorates as you go up the scales, and therefore, the scalogram kind of diverges as you in terms or spreads in time as you move up the scales and becomes narrower as you move down the scales. So, this is something to keep in mind, because and this is of particular interest, because what happens is when we compute CWT, we are computing CWT of a finite length signal, and we have talked about this earlier also in different contexts, particularly in the computation of CWT. We have edge effects whenever we compute CWT. So, at the borders, what happens is you are essentially running into discontinuities. If you are using a convolution algorithm, then it assumes something about the signal beyond outside the observation interval, and if you are using an FFT based algorithm, it assumes that the signal repeats itself and so on. In fact, with the convolution algorithm, you can change the assumptions that you want on how the signal behaves outside the observation interval. But normally what happens is eventually when you are computing the CWT of a finite length signal, the wavelet really is not seeing the signal, is unable to see the signal outside the interval. If you extend it, then it will be able to see it, but whatever may be the extension, there are going to be edge effects, and how these edge effects decay depend on the extension. If you do not perform any extension, then that is, in the sense you assume that the signal to be 0 outside the interval, then you have discontinuities occurring at the edges. In other words, as if the wavelet is seeing an impulse located at the beginning and at the end of the signal. What is the impact of this discontinuity on the scalogram? Well, the impact is straightforward. In fact, this is captured in what is known as a cone of influence. The impact is very can be intuitively understood. When I use a wavelet of high scale, that is wide wavelet, then when I am situated either at the beginning and the end or the end, a huge portion of the wavelet is outside the observation interval. In other words, when if I want to really analyze the signal properly, I have to make sure that the entire wavelet is located within the observation interval. For wide wavelets, it takes a long time for the wavelet to really that is the entire width of the wavelet to be within the observation interval. For narrow wavelets, their width is narrow, therefore, it does not take too long for that, too long meaning as you are traversing along the signal, it does not take too long for the wavelet to come within the observation interval. Let me show that to you on the board. So, look at this here, this situation. When I am using a wide wavelet, then essentially what is happening is, let us say this wide wavelet was initially located at this point, then this would how the wavelet look like initially, that is when I am looking at tau equals 0. So, what is happening is there is a huge portion of the wavelet, large portion of the wavelet outside the observation interval, and this produces artifacts in your CWT. Of course, depending on how you extend the signal outside the interval, but if I assume that the signal is 0, then you are introducing a discontinuity at this point and at the end points. So, the artifacts that are produced by this wide wavelet at this point is more or less the same as the wavelet of an impulse located at time 0. What we have seen earlier in the example is an impulse located at 80th instant, and we noticed that the energy is spread in time quite heavily. So, what happens is here the effect of the discontinuity is felt for a long time. Intuitively, how long? Well, the time it takes for the wavelet to be completely within the interval of the signal. Now, compare this with the situation of a narrow wavelet. So, let us color it differently here. The narrow wavelet is red in color. imagine this narrow wavelet being placed here, that is at the beginning of the signal, so that the center of the wavelet is exactly at the origin. Once again, of course, you have a portion of the wavelet outside the signal's observation interval, but the time for this wavelet to be drawn within, that is to within the signal's observation interval, is not going to be too long. Right. For small values of tau, the wavelet is going to be completely within the signal's interval. It is the other way of saying that is, if the energy spread of an impulse located at the origin obtained from a high frequency wavelet is not going to be spread too much in time, as we have seen in the previous plot. Therefore, the time for this effect of discontinuity to be felt at finer scales, that is lower scales, is going to be much smaller. Now, these times that are taken by each of these wavelets at different scales for the effect of discontinuities to vanish are called E folding times, and this E folding times can be calculated for different wavelets. It is given in the paper by Torrance and Compo and so on. Rather than worrying about exactly the E folding times, hopefully you have understood the concept of this influence, time of influence of these discontinuities at the edges. And normally what happens is, when you look at it in the scalogram, these appear as the that is, there is a cone of influence that can be drawn, and only the scalogram values within that cone can be considered for any statistical analysis. The values outside the cone of influence are cannot be subjected to any particular statistical analysis, because there are quite a few artifacts introduced by the discontinuities at the beginning and end. In MATLAB, you can calculate the cone of influence using a routine called CON of INF, but using that and along with the scalogram plot is not so straightforward. Instead, you could use the open source wavelet toolbox by Grinstead and Moore. That toolbox supplies essentially a routine called WT, which computes a CWT, and using that we can obtain the cone of influence as well as the scalogram. So, let me just show you that show you how to do that with that routine WT. So, you have to install the wavelet toolbox, which is freely available from Grinstead and Moore's website, or of course, you can use the CON OF INF routine that is available with the wavelet toolbox. But I find using the WT routine from the package by Grinstead and Moore much easier. Therefore, I will just show you. It is called the WTC toolbox, wavelet coherence toolbox, and bundled with that is this WT command, and simply invoking WT, for example xk on the previous signal that we had produces a scalogram as well as the cone of influence. So, look at what we have here. What is plotted here on the y axis, let me enhance the y axis. Font sizes for you, hopefully now it is a lot more visible, or maybe I can just change it to. Okay. So, what we have here is period, which is nothing but equivalent of scale, and this scalogram has been computed using the complex Morlet wavelet. This is a normalized scalogram, and what you see here is a cone of influence. Without the cone of influence, it is hard to find out which parts of the scalogram can be subjected to scientific analysis or statistical analysis. Now, with this cone of influence, what I know is at low scales, that is at low periods, the scalogram values calculated at these times, that is starting nearly from 0 to the end of the signal, are reliable. There are no say artifacts there, or the artifacts introduced by the discontinuities at the edges vanish in no time. Whereas, when you come to high scales, that is high periods, the time taken for the edge effects is longer, and therefore, I have to wait for quite some time before the wavelet is completely drawn into the observation interval, and hence the scalogram values available or reliable scalogram values are only over a narrower period of time. So, always one should use this cone of influence when you want to make meaningful interpretations out of a scalogram. Of course, in this case a scalogram outside the cone of influence also corresponds to what we see in the signal features, but then the scalogram values outside the cone of influence are influenced by the discontinuities at the edges, all right. So, this is what I wanted to show you in this lecture, and of course, we have looked at the definition of scalogram, and now we have learned how to do this in MATLAB. And what we shall do in the next lecture is we shall talk of an interesting cousin of wavelet, which is a wavelet function, which is called the scaling function, where we will introduce essentially the low filter equivalent of the wavelet function. A wavelet acts as a band pass filter, but it is nice to have both the low frequency filter and the band pass filter, so that we can traverse the entire frequency range. And see you in the next lecture.